How can feedback control systems handle parameter variations? Imagine trying to steer a boat through choppy waters. No matter how the waves change, you keep adjusting the rudder to stay on course. That's similar to what feedback control systems do with changing parameters. They constantly measure what's happening and make real-time adjustments to keep everything steady. When a system's components change or external conditions shift, feedback control helps the system adapt automatically. This is especially useful in electrical engineering, where component values or environmental factors can vary unexpectedly. A feedback control system has four main parts: the plant, which is the system you want to control, sensors that measure the output, a controller that decides how to adjust based on the error, and actuators that apply those adjustments. The error is the difference between what you want and what you actually get. The controller uses this error to change the input so the output moves closer to the target. If the system's parameters change, the feedback loop detects the deviation and corrects it by tweaking the input. Think about a voltage regulator in a power supply. If the load increases or the input voltage drops, the feedback system notices the change and adjusts the output voltage accordingly. This way, the voltage stays steady despite variations. The mathematics behind this shows that the system's overall response becomes less sensitive to parameter changes because of the feedback loop. For example, the system gain is modified by the factor of 1/1 plus the product of the forward gain and the feedback gain. This means the system can handle changes in component values without losing stability or accuracy. Negative feedback is especially good at reducing errors and stabilizing the system. It subtracts part of the output from the input, which helps correct deviations caused by disturbances or parameter shifts. This not only keeps the system stable but also improves how quickly it responds and how accurately it reaches the desired output. In electrical systems like motor speed controllers, feedback helps maintain consistent speed even if the load varies. In communication systems, it ensures signals stay clear despite interference or component drift. Advanced control methods like proportional integral derivative controllers tune the response to errors, making the system even better at handling parameter changes. Combining feedback with feed-forward control, which anticipates disturbances based on measurements, can further improve performance. So, in essence, feedback control systems handle parameter variations by continuously measuring the output and adjusting the input in real time. This keeps the system stable, accurate, and reliable, even when things change unexpectedly. It's like having a smart autopilot that keeps everything on track no matter what the environment throws at it.